Now we're going to introduce another key idea in the mathematics of quantum mechanics. This is the idea of operators. We will find that for every physically measurable quantity in quantum mechanics, there's an operator. For example, for momentum, which is measurable, there's a momentum operator. For position, there is a position operator. For historical reasons, the operator associated with energy has its own name, the Hamiltonian. We're going to find that operators are extremely useful in the mathematics of quantum mechanics. We're going to start here by introducing the Hamiltonian operator. We're going to be able to use it right away for a very cute trick, a particularly easy and general way of finding the expectation value of the energy for some quantum mechanical state. So let's look at the Hamiltonian operator.
In classical mechanics, the Hamiltonian is a function of position and momentum, and it represents the total energy of the system. In quantum mechanical systems that we can analyze using Schrödinger's equation, so that means anything with mass and non-relativistic, we can define the entity, this h with a little hat over it, as what you'll see is really part of Schrödinger's equation, but we'll define this entity, minus h bar squared over 2m del squared plus v, the potential of r and t. And if we do that, just as a shorthand, we can rewrite the Schrödinger equations as h with this little hat operating on psi of r is equal to E times psi of r. That's our time-independent Schrödinger equation. And our time-dependent Schrödinger equation, the same thing on the left really, and I h bar d psi by dt on the right-hand side here. Now, this entity that we've just written down, an h with a little hat on the top, it's not a number, it's not a function, it's an operator. And another operator that you're very familiar with is something like the spatial derivative operator, like d by dz, for example. And we are going to use the notation with this hat up on top to indicate that we are dealing with an operator. We're not going to rewrite these kinds of operators by putting hats on them, but for everything else that we come across in general, we'll be trying to put a little hat on top to indicate that we're talking about an operator. What is an operator? The most general definition of an operator is something that turns one function into another. So you know that when you have d by dz and you operate on some function, you get a new function, the derivative of the one that you started with. So that's an example of an operator turning one function into another function. And this Hamiltonian operator here does exactly the same kind of thing. It turns one function into another function. Now, this particular operator that we've been looking at so far, h with the hat on it, is called, of course, the Hamiltonian operator. And just like the classical Hamiltonian function, it's the operator that is related to the total energy of the system. And this idea of the Hamiltonian extends beyond the specific Schrödinger equation definition we have so far, which was for single non-magnetic particles. In general, in non-relativistic quantum mechanics, the Hamiltonian is going to be the operator related to the total energy of the system. So it could be something somewhat different from the Schrödinger equation-like version of it we've seen so far. We could be talking about photons, or we could be talking about many other things, and we would be able to still talk about the Hamiltonian as being the operator related to the energy. Now, why are we introducing this idea of operators? Well, here's one very important particular reason why we do it. There turn out to be many reasons why we like to work with the mathematics this way, but this one is very practically important. We're going to be able to show a simple and rather general relation between the Hamiltonian operator, the wave function, and the expectation value of the energy. To do so, we're going to start by looking at this integral here. So it's the integral with the wave function of the system on the right, the Hamiltonian operator in the middle, and the complex conjugate of the wave function operator on the left. And we're going to integrate that over all space. And psi of r and t is the wave function of some system of interest. So we're presuming we know this wave function, and we're going to work out this integral here. Remember, this h is operating on this psi in here. In general, it's taking this psi and turning it into another function. And we're taking the integral of whatever that function is now, multiplying it by this and integrating it all up. In looking at this integral that we have here, we're going to expand this wave function and also this one in the normalized energy eigenstates of the problem, whatever those are. So we presume for the moment that we can know these energy eigenstates, psi n of r, and we're going to expand this function and also, incidentally, this one in those energy eigenstates. So here's our expansion. Here are the energy eigenstates. There's some coefficients as a function of time that go in front of them here. Any function that's going to be a solution of our Schrödinger equation as a function of time can certainly be written this way, because at any specific time, we're just doing an expansion in this complete set. So we can rewrite this right-hand side part here, these two little bits. For example, if we think explicitly for the moment about the Schrödinger equation form of the Hamiltonian, although we don't have to restrict ourselves to that. But we know if we take this form here, operate on the wave function, then we'll be doing this operation. We'll be taking our Hamiltonian operator, operating on this expansion here. And the operator, the Hamiltonian, operating on one of the energy eigenstates gives us En times that energy eigenstate. And we're saying that's generally true, not just for this very specific Schrödinger equation form of the Hamiltonian, but in general, if I take the Hamiltonian and operate on an energy eigenstate, I will get En times that same energy eigenstate, psi n of r. So these two parts on the right-hand side of the integrand here, we can rewrite them like this. So the integral overall now becomes what we just had concluded. It's En times the energy eigenfunctions in here inside this sum. And then this is just the expansion of the complex conjugate of the quantum mechanical state, the psi n of r and t complex conjugated. So we've broken this integral here down into an integral of a product of two sums of terms. And of course, we have to remember to use a different index in this expansion from what we used over here in the expansion of psi n of r and t itself. Now, because of the orthonormality of the basis functions psi n of r, the only terms in this double sum here that are going to survive once we've done the integral are going to be the ones for which n is equal to m. So when we do that, we're only left with these terms where m is equal n, and looking at all of those terms, each one of them is just Cn squared, the modulus of Cn squared. And so the result for this entire integral here is the sum over n of En Cn squared. But we recognize that this is just the expectation value of the energy. So we have a way of writing down the expectation value of the energy. This integral here, with the Hamiltonian operator in the middle, operating on the wave function on the right, and multiplying the result of all of that by the complex conjugate of the wave function, and integrating over all space, gives us the expectation value of the energy. So why do we want to do this? If we already knew how to calculate the expectation value of the energy, and we certainly did, from this expression here where we had figured out all these expansion coefficients on the eigenfunction basis and modulus squared of them times En, we had this formula already. This was the probability from Born's rule. Why do we want to do this? Why do we want to use this new relation? The answer to that is we don't even have to solve for the eigenfunctions of the operator to get the result. So we've used those in the proof, but we don't have to use them when we come to do the calculation. If we know the state, if we know the operator here for energy, we can work out the expectation value of the energy directly from this integral. We don't even have to do that expansion in the eigenfunctions.
This particular trick of using the operator associated with some measurable quantity together with the state of the quantum mechanical system to allow us to evaluate the expectation value of some measurable quantity, this trick is quite general in quantum mechanics. We illustrated this here with the energy operator, the Hamiltonian, and with the evaluation of energy. But we will keep coming back to this as we introduce the operators for other physical quantities. This trick, and the use of operators generally in quantum mechanics, are very important aspects of quantum mechanics, and we will keep coming back to these ideas and manipulations again and again as we develop our understanding of quantum mechanics.